I hope to see many of you. I hope to make many new friends tonight. And if you're joining and you regularly join, I also hope to see you. I don't know what happened to my voice right there. But yes, good morning, good afternoon, good night. How is everybody doing? I promised that I would talk to you about active galaxies. Last night's live was amazing. I got so many relevant questions and interesting questions that I felt like I should answer. And most of the live was about that. I did touch upon the active galaxies topic a little bit, but tonight I'm back. And depending on how the live stream goes, of course, I will talk to you about these active galaxies and quasars particularly. Especially, let me get this particular information out of the way before, while I can. Active galaxies have many distinctive attributes and they're kind of different from normal galaxies, and one of them is that active galaxies have much of their light concentrated in a small central region known as the active galactic nuclei, or AGN. So I'll put that out there and I'll wait for more people to join. Hello, welcome. Welcome, welcome. How are you? Say hi, ask a question, say hello. If you are joining, welcome. If you're seeing this as a video upload later on, also welcome and thank you. And please do leave me a comment, and that would be wonderful. And I'll keep going for a little bit. Let people join as they come in. So active galaxies produce large amounts of non-stellar emissions. So you know how a lot of the normal galaxies that we've been talking about, more I guess common galaxies. We talked about the galaxy classification system and how roughly we had spiral galaxies, elliptical galaxies, and irregular galaxies. And we have live streams on all of these in the past few days. Active galaxies are going to be a little bit different. And remember that for those usual type of galaxies, remember the big thing was to understand what was the total luminosity of the galaxy. And of course, most of that luminosity was coming from stellar luminosity. So we actually talked about the galaxies colliding last night. We can briefly talk about that real quick, actually. That's a great question. Hello. Hello, Rouge One. How do galaxies rotate? What happens when galaxies collide? So basically, within a galaxy, there is a lot of the spiral galaxies and the galaxies that we're familiar with has a supermassive black hole at the galactic center, and all of the other stuff in the galaxy, such as us, even we are orbiting the sun, and the sun is orbiting this galactic center. And we even learned that the sun, actually being a pretty young star at only 4.6 billion years old, has made around 20 trips around our own galactic center. So that's something to address about the rotation, if that's what you meant about the galaxy, within galaxy rotation. And then galaxy collision, we actually talked about some particular things that would happen. One of them is that you might think that the stars within each of the galaxies would collide with each other, but that's not going to happen. The chances of that happening is pretty low. And the other thing is that the gases within each of the galaxies would actually collide, because the cross section for that collision is pretty high. And it would actually make the collided or the merged gas more enriched and promote more star formation. So when two galaxies collide, we don't expect that the stars would collide within them. And we do expect that the gases would collide and perhaps make the galactic gas, the interstellar medium, more enriched and promote more star formation. So that's pretty exciting. Let me say hi to everybody real quick. So, hi Rouge One. Thank you for joining and thank you for your question. We will keep talking about it for a little bit. Hi Daniela. What's your name? My name is Baji's mom. So, Baji's the kitty cat on the channel and I'm his mom. Shadow Kingdom says, hey guys, it's me and back with another ghost hunting video today. Hi, Shadow. Hi, Daniela. Hi, Augusto. Hi, Steven. Steven, hello. Fuji. Fuji's playing with his toy, his nightly playtime. Hi, Fuji. Fuji's playing with this toy. Fuji's my son who is a cat. And he's playing with this toy and I'm trying to give him encouragement during the live stream. Sorry about that, but you know, I have to talk to my children as well. Hey all, good morning, Stephen. R, how are you? So Daniela, thank you again for being here. Augusto, are you teacher? Yes. And okay, so I'll keep talking to you about the question that Rouge One asked. What types of stars are there? How long do stars live? So, okay, that's a great question. So in our own galaxy, so you have to be specific which galaxy you're talking about. So we've spoken a lot about the spiral galaxies and sort of the different components of a spiral galaxy. So I'll briefly recap that. So spiral galaxies have three main components: the disk, the bulge, and the halo. So the disk has a lot of super duper more star forming active regions and sort of the newer stars, population 1 stars or metal rich stars, whereas the halo has a lot of the older population 2 and metal poor stars. And then we also talked about the bulge, which has certain intermediate type of stars as well. So it depends on. Hi, Sundar. Sundar says, love this gal. Thank you. Farooq says, we wouldn't know because we're... Okay. Well, we would know quite a bit, actually, depending on our observations and things like that. And I'm talking about our own galaxy. We know a fair amount, actually. And especially from something like spectral data, you can actually figure out what types of metals there might be in a certain star and things like that. Lenticular galaxies. Is that a question about lenticular galaxies? Please give her more likes, guys. Thank you. Oh, that's so nice. Thank you, kind of you, Sundar. Unknown says, I am back. So let me give you the answer to the first question you asked. I thought that was a very good question. And by the way, if you're interested in my Galaxy live streams, you can go back to the previous live streams. I cover a lot of material. On galaxies and the different types of galaxies, the classification of galaxies. Today's topic is going to be active galaxies, so that's what I'll get into in a little bit here. But we've already kind of proved what proves metals are there within a galaxy. So it's actually within the stars. So depending on spectral data of the stars, you can figure out whether it's metal rich or metal poor. So the main sort of on-so-said planets, I always, so let me, 1 second. Let me make sure I'm not losing somebody. I was waiting for you to come on tonight. Always nice to chat with you and my new friends. Oh gosh. Hi, Steven. I always wondered how astronomers and physicists know what our galaxy looks like. Just curious if you could explain it. Yeah, so I don't know if you were here when we were comparing our own galaxy with a couple of other spiral galaxies. We talked about certain comparisons. We saw at a picture edge on versus face on. So we have a pretty good idea. So because we're within the Milky Way galaxy, we can't take a picture of it because we'd have to go outside. So we can't really see our own galaxy edge on or face on, but we know a fair amount about our galaxy. We know, we're part of the disk. We have a lot of data. We know the galactic center is really bright in radio waves. So we have a lot of observations, and we also know that the halo is spherical. It goes around all over, and it has the more metal poor stars. It's all from mostly the spectral data. If you have spectral data and you don't see the lines missing for something, say for calcium, then you know that calcium is not within that star. So things like that, and it kind of also matches with our sort of understanding of how things evolve. So for example, the spiral galaxies have these big spiral arms. Let me get to the picture. In the big spiral arms, there are some hotbeds that we call of star formation regions. And those are pretty, those are kind of where I've been camping years ago and got a great view of the night sky without. Yeah, so if you go to somewhere dark, hopefully you can see the Milky Way galaxy. So this is our galaxy, an artist's impression of our galaxy. And let me real quick show you the pictures of two other galaxies. So these are images. So I don't know if you can see very well, but one of them is an edge-on image, and the other is so this is an edge-on image, and this is a face-on image. So these are actual images taken of NGC 891 and M83, and these are also spiral galaxies. Those kind of help us with the comparison of, I'll get to that question, but those kind of help us with other spiral galaxies as well. And then before I forget, let me answer about the galaxy collision. So we spoke about it yesterday, but I just want to summarize it. There's a really nice summary here, and this is the book, which is called Foundations of Astrophysics by Barbara Ryden and Bradley M. Peterson. Ooh, another picture I wanted to show you. So if two galaxies merge, sometimes this is sort of what it might look like, where the two galaxies are basically putting tidal forces on each other. And it's almost like catching hold of a tail, if you will. It's kind of like give me your tail, I'll take your tail. And then sort of the material starts to come together, merge more and more. It's like grabbing onto someone by the tail and slowly pulling each other in, and then that ends up being ends up being the merge of that galaxy. So what I just showed you is a recently simulated galaxy encounter. And we're going to do that sort of thing with Andromeda. So we talked about our merger with Andromeda. So let me quickly talk about that, because that was the initial question that Rouge 1 asked about the galaxy mergers. So here's a nice summary. So things to remember when galaxies do collide. Individual stars we don't believe will collide with each other. There will not be a sudden bonanza of blue stragglers. Galaxy collisions are inelastic. So remember the inelastic. So if there's two objects, inelastic collision is like when they stick together like this. Elastic collision is when they bounce apart. So galaxy collisions are considered to be, collisions are considered to be inelastic. That is, during the collision, some of the orbital kinetic energy of the galaxies is converted to internal energy in the form of random motions of the stars. Thus, a pair of galaxies that start out on a hyperbolic orbits relative to each other can still end up as a bound system. Yes. Yeah. We will be the Milky Way galaxy, and then we won't significantly merge with Andromeda until about 3.2 billion years later, and then in 6 billion years or 6 giga years, we will have the merger with Andromeda. Next point about galaxy collisions is that although the stars don't collide, the gas clouds do collide within the galaxies. So a giant molecular cloud has a radius of around 10 parsecs, 10 parsecs. So that's around 4 times 10 to the 8, the radius of our sun, for example. And the large cross section for molecular clouds mean that the gas clouds will collide when two gas-rich galaxies pass through each other. Does time act the same here as other galaxies? So that's a great question. So according to general theory of relativity, it's really about where, if you're near a very massive object or not. So it's not so much about the galaxy, but are you near a very massive object, because that's going to bend space-time differently. Okay? Thanks to the colliding gas clouds, merging galaxies are hotbeds of star formation. So this is the main thing that you can expect when two galaxies collide, is that it will actually lead to new stars forming. So, even our sun came from a nebula, like the sun and the planets in our solar system came from a pretty enriched gas cloud. So the sun has calcium in it. So like it's not a metal poor star. It's burning hydrogen to make helium. So it's doing a pretty basic nuclear reaction, but it also has other elements in it. How do we know? You would get spectral lines from something like the sun. You can look up spectroscopy, and pretty much if the energy is absorbed by a certain element, it will show up as a line or a missing line, an absorption line, basically. And that's how we know, oh, wow, so the sun actually has, for example, calcium. And from these spectroscopic lines, we would know. So that's because we come from, all of us, we are all coming from some gas cloud, which ultimately condensated to make the sun and the planets. And we actually talked about the planets a lot in some of the lives as well. So when we talked about planetology and how our solar system was made and planets and everything like that, and comparison of all the planets, so I had a number of lives on this a few lives ago. Then I got into galaxies. You will see that we talked about how different planets formed at different distances from the sun, but all of us like kind of formed in the same plane, and we all orbit in the same plane and all of that, because we literally come from some nebula, and most of the mass of that nebula went to the sun. So 99.8%, but check my number, of the mass of that nebula went to the sun, and only like 5% of the angular momentum went to the sun, and all the rest of the angular momentum is within us, the planets. So that's why the planets are rotating a lot faster, and a lot more of the angular momentum is within the planets. So, the gas clouds, it may sound kind of boring, like galaxies, gas clouds, but actually, first of all, did you also know that there's a lot of mass? There's more mass in gases than in stars. There's just a ton of gas actually in all of these galaxy. The edge of the universe stop growing. So there is no edge, actually. There is no edge that we know of in the universe. I just saw the question real quick, so I thought I'd quickly answer, and I'd get back to my the star stuff. But it's extremely important to appreciate, even though gas clouds and gas as an interstellar medium is something we don't talk about too much, but actually that interstellar medium being enriched is very important. And in fact, this is why supernovae are important. When stars die, when they explode, what's happening is they're putting all their material that they just spend their whole life making. Like, for example, they could have burned hydrogen to helium like our own sun, or they could have made carbon and oxygen and further higher and higher, heavier elements. They could have if they have an iron core, then they have done a lot of nuclear physics, right, within their lifetime. And when they explode, there is a lot of material that's going everywhere in terms of the stellar winds. We talked about core collapse supernovae as well in the past. So there's more details in that particular live. But basically, sometimes during a supernova, the star will lose a lot of its material even before it has completely collapsed through stellar winds. And remember, all of these processes and ultimately the explosion and everything, shock accelerations and shocks with even the interstellar medium, is basically putting material into the interstellar medium. And why is that important? Because that will make metal-rich gas clouds, where in astronomy, anything above helium is a metal. So even if you made lithium, carbon, boron, beryllium, anything, nitrogen, we love it. Like in astronomy, we say that being metal rich is just having any element. Pretty much if you have significant elements over helium, then that's pretty good. That's metal rich. Why do we say metal poor? Because remember, the very old stars, the first generation of stars that were formed in the universe would be metal poor. Why? Because remember, we talked about cosmology, and we know that in the Big Bang nucleosynthesis, as far as baryons go, we just made hydrogen and a little bit of helium and very trace amounts of lithium. So the first stars did not have stars before that to help them have more stuff to begin with, more types of metals to begin with. They were literally happening from the baryons that were available back then, which was mainly just hydrogen. Even now, the most abundant element in the universe is just hydrogen. That tells you something, right? Which is that hydrogen is what you can expect in the universe. Like these stars don't have, the first stars, the population 2 old stars, those don't have a ton of metals. They would just mainly have hydrogen and maybe a little bit of helium. So that's what I mean by the metal rich, metal poor. But this is incredibly important. The merging of galaxies too is another way in which the interstellar medium can get more metal rich. And then the nebula that would form, and then that nebula would cool down and, make a new star and planets, maybe just like our solar system formed, something like that. Maybe something, not every time will be the same way, but that is incredibly important, because then that will lead to the future solar systems, future star systems, right? So even our galaxy will do that with Andromeda, and that will enrich our gases, our interstellar medium further. And who knows what types of star systems will form, what types of planets will form, and what types of aliens will live on them in the future, okay? So the class of galaxies known as ultra-luminous infrared galaxies are frequently found to be merging galaxies in which large numbers of dust-enshrouded protostars, so sort of like the beginning of a star, produce copious amounts of far infrared light. Merging galaxies also produce lots of blue and ultraviolet light, thanks to the large number of O and B stars produced. So these are pretty hot and happening stars. The merging galaxies, known as the antennae, attribute to their long tidal tails. So those tails I showed you in the picture just now, those long tidal tails, because the merger is not going to just happen suddenly, right? It's going to take time. Actually, it's going to take billions of years, as we will find out, for example, with Andromeda. And it's really about those tails and kind of getting that antenna shape happening. So actually, let me see. The antennae, the merging galaxies known as the antennae, are 14 megaparsecs away in the constellation Corvus. So sometimes, so there's already examples of this happening already. The antennae are very luminous in their central regions, both at blue wavelengths and at infrared wavelengths. So this is some other example of a merger. We will also talk about our own galaxy's merger. And sometimes this is called, if a galaxy that's bigger is kind of merging with smaller galaxies nearby, it is called galactic cannibalism. Basically like a bigger thing eating the smaller things nearby. So galaxy mergers are like car crashes in that they are very effective at increasing entropy. So we know that entropy always increases, and that would just happen more with a galactic merger. Galaxies differ in the amount of entropy or disorder they contain. Spiral galaxies, so this is important, by the way, or interesting, we talked about how mainly we have spiral galaxies, elliptical galaxies, and irregular galaxies. We will also talk about active galaxies. It's kind of different, which has the active galactic nuclei and quasars. So that's kind of different. So if you forget about active galaxies for a minute, we know that the galaxy shapes are spiral, elliptical, and irregular. But what happens when a spiral galaxy merges with, say, another spiral galaxy or something? So we're going to talk about that. So spiral galaxies contain stars on orderly, one-way, nearly circular orbits. Spirals are low in entropy. Elliptical galaxies contain stars on disorderly, randomly oriented orbits. Ellipticals are high in entropy. When two neat, orderly, compact cars collide, you don't get a neat, orderly SUV, you get a disordered heap of rubble. Similarly, when two neat, orderly spiral galaxies collide, you don't get a neat, orderly giant spiral, you get a disordered heap of stars, otherwise known as an elliptical galaxy. So I was sad the other day because I realized that when we merge with Andromeda, we're not even going to remain a spiral. So listen to this. The giant elliptical galaxies in the centers of rich clusters, so cluster of galaxy. We talked about what a cluster is earlier as well. Like NGC 4889 and NGC 4874 are elliptical galaxies in the middle of the Coma cluster, have grown to their present large size by the process of galactic cannibalism. The cannibalism refers to the fact that when a large galaxy merges with a small one, the large galaxy retains its identity while the smaller one is disrupted. Sometimes partly digested, cannibalized galaxies can be seen as multiple nuclei within a giant elliptical galaxy. So this is where some of the irregular galaxies come from. The classification irregular galaxy comes from. Sometimes it's literally a merger that's left a galaxy looking plain weird. And when we see it and we're like, what is that? It's a cannibalized galaxy or a cannibalizing galaxy. Our galaxy, also a cannibal. So we're a pretty big galaxy. We have a substantial size and we have a ton of stars. We have 200 billion stars. Our luminosity, total luminosity is around 23 billion, but the solar luminosity that is, and our number of stars is around 200 billion stars. So what that tells you is that we have a ton of dimmer stars. Not every star is like the sun. Our sun is a pretty bright young star. There are stars that are much more dim, metal poor in the halo and things like that. So, you know, but anyways, what I'm trying to say is that our galaxy has a lot of diversity, variety. It's a big, substantial galaxy. So it's gonna also be a cannibal. So our galaxy is a cannibal as well, but only on a low level. And oh yeah, I see some comments about Sagittarius. We're going to talk about actually a dwarf galaxy in that name. But yeah, Sagittarius A star is the supermassive black hole. Did someone ask? Yes, so we have a supermassive black hole called Sagittarius A star. We can talk about that as well. Why is it so bright? It's because it's accreting materials from its neighboring objects and the falling material that's being eaten. So supermassive black hole is a black hole that became bigger because of eating more stuff. A normal black hole, say from a star exploding and becoming a black hole, like we've talked about, like stars ultimately die, they supernova and they leave behind a compact object, which is either a white dwarf or a neutron star or a black hole. So that's sort of the normal way of a black hole forming. But if such a black hole, say, finds a way to continually eat more material, then it could grow to the size of a supermassive black hole, like our supermassive black hole at our galactic center. And we think, we have reason to think that there are many galaxies have such a galactic center, which has a supermassive black hole. So our supermassive black hole's name is Sagittarius A star. We will talk about it as well, since there's some interest in it. And it's very bright around our supermassive black hole in radio and X-rays. We will talk about that. But real quick, the reason for that is because of the falling material into the black hole. As you know, a black hole does not let light escape, so it's dark. It used to be called a dark star. Now we call it a black hole, but it's literally a compact object that is, in the case of the supermassive black hole, it's very, very massive. We will talk about its exact mass, but there are certain sort of requirements to be a black hole, right? In the case of one of the main requirements is that even light cannot escape it. So if you enter the event horizon, and we can define what that is, of a black hole, you're not going to be able to come back out. So if you want to fall into one, just be sure that you want to do that and not come back, because you won't be able to come back. So the supermassive black hole, sometimes, or just in general, other black holes too, could sometimes, like, even though it doesn't let light escape, it could be bright around it, because, and giving away that there is a black hole there, because it's still accreting stuff into it. It's still eating stuff into it, or stuff is falling into it, and that accelerating falling material is bright in radio waves and other wavelengths of light. So that's how we know about supermassive black holes. And yes, the particular name of our own supermassive black hole is Sagittarius A star. But we will also talk about the Sagittarius system in general. Like, there's a few different parts to it, Sagittarius A West and all that stuff. We'll talk about it. Yes, you will be crushed, but how you will be crushed is also something we can talk about. So depending on the tidal forces on you as you're falling, you could be crushed before or after. So we actually talked about that in the past as well. We've talked about the supermassive black hole in the past already, but we can do so again. Let me finish about our galaxy's merger with Andromeda. There's a lot of really good questions here. So, but yeah, how you get crushed is also specific. It depends on the tidal forces on your body. So if you want to see the inside of a black hole, there is a strategy with which you could fall into a black hole. You just have to tell me your mass and the black hole's mass, and we can figure something out for you if you want to see the inside of it, if you will. There is a discussion about that too in this book. So if you are crushed too much while you're falling, then of course you'll die before you see the inside of it. But there is a strategy in which you could try to minimize the tidal forces on you. Okay? So our galaxy is a cannibal as well, but on a low level, as in we're not cannibalizing too much. It is currently tidally disrupting a few dwarf galaxies. So we do eat some dwarf galaxies now and then, but we're not too big of a cannibal. Because we've just disrupted Sagittarius dwarf galaxy. It's a name of a dwarf galaxy, a small galaxy, and the Canis Majoris dwarf galaxy, which are disintegrating into long tidal streams, like we mentioned, that will eventually be mixed in with the halo of our galaxy. So because our halo is, it goes around. It goes around for a while. So even though our galaxy is not, it's not the same everywhere. There's the spiral arms, there's the bulge, the supermassive black hole at the center. Then there is the different arms, the disk and all that. But the halo is right there. And so the halo has mass and, does its own gravitation. And so it is currently tidally disrupting these couple of dwarf galaxies, which are basically disintegrating into long tidal streams, and pretty much before, without too much drama, they will basically merge with our halo. So it's not like, oh, there's a big deal, there's a big deal dramatic encounter, really. If something becomes a long tail, and it's much smaller of a galaxy, and ultimately it merges with our halo, that's not that dramatic, right? It can just happen. We wouldn't know. Like, for example, we're not in the halo. Do we care? Maybe not. These minor encounters are trivial in comparison to our upcoming encounter with M31. So M31 is the name of Andromeda. Andromeda galaxy is that's going to be a major merger. and it's blue shifted with respect to the center of our galaxy. The relative velocity of the centers of the two galaxies is negative 123 kilometers per second. The tangential velocity we don't know, thanks to the difficulty of measuring proper motions at large distances, but it's likely to be small. Thus, in a time of what we think is going to be around 6 gigayears or 6 billion years, M31 and our own galaxy will merge. Andromeda and us will merge. And we have some simulations on this already, and it's indicating around 3.2 gigayears is when the two galaxies will have a close passage, inducing the long tidal tails. So that even the long tidal tails will take some time to form. Because once you have those tidal tails happening, pretty much the merger is inevitable. All of it is inevitable. It's going to happen. The two distorted galaxies will fall back toward each other. About 4.6 gigayears from now, they will have merged a large elliptical galaxy. So two spiral galaxies will form a large elliptical galaxy surrounded by tidal debris when the sun becomes a red giant. So this is where I'm sad. When this happens, that is the timeline of the sun becoming a red giant. So we will probably die, and at that time our galaxy will basically be part of a large, it will be an elliptical galaxy. So when the sun is a red giant, we will be a member of an elliptical galaxy, not a spiral galaxy. So right now we're a beautiful spiral, but by the time we merge with Andromeda is also the same timing of the sun becoming a red giant, probably making it difficult for us to survive. And that is when the galaxy's shape will change. It will go through so much change and become an elliptical galaxy, which is a completely different shape galaxy and everything. And so enjoy the spiralness of our galaxy for now. Enjoy the sun as a main sequence young star for now, because everything is always changing. And that makes me a little sad that those changes will happen and we might not be here at that time. Hi, Crazy Sick Wine. Sundar asked, how does a galaxy form? That's a very good and difficult question. Let's talk about Sagittarius A star really quickly, because I see some questions about it. Hopefully I covered something that helps with the merger question, 462. Let's talk about our own supermassive black hole real quick, okay? Because it's important. Okay, it's called the nucleus of our galaxy. Oh yeah, we are super interested in space and astronomy. So I go live every day, almost every day, every night, sometimes in the afternoons too, and I cover cosmology, astronomy, astrophysics, and physics. And I've already covered supernovae, novae, like nova versus a supernova. Those different things. A nova is like when a white dwarf is getting piled on by a companion star. A supernova is a stellar death. There are 3 types. We talked about that. We talked about stellar remnants, what happens to stars when they die, what they make, white dwarf, neutron star, or black hole. We've talked about tidal forces by a black hole, like I was talking about with, we can do the math about how crushed and how you will be crushed if we just dealt with the masses of the two things, the person and the black hole. So we've kind of covered all those topics already. At a regular basis, I also talk about the universe's evolution from the Big Bang to the current state and what is the cosmic inventory and cosmic ingredients of the universe as well. So that's another well-liked topic, I think, the Big Bang, nucleosynthesis, as well as the cosmic inventory of photons, baryons, neutrinos, dark matter, and dark energy. So we've also spoken about the expansion of the universe and how, dark energy, that's what that is. And also dark matter, what that is. Well, we don't know what it is, but we talked about what do we know so far. So 2 biggest open questions of the universe right now: what is dark energy and what is dark matter? We've explored these topics as well. So this is sort of the vibe. We talk a lot about astronomy, astrophysics and cosmology as well. Let's talk about the supermassive black hole at the center of our own galaxy because there are some questions I see. I think the large and small Magellanic clouds are being eaten by the Milky Way. We can talk about that. Those are, yes, unknown. The lights at the super black hole is not a strong hole to suck up the light because it's a black. Yeah, so it's bright around we will talk about it, but it's bright around the supermassive black hole because of the falling material. The falling material is being accelerated, right? So the supermassive black hole is a very extreme environment. Like we are, we go around the sun, we experience the gravitation of the sun. We will find out how massive the supermassive black hole is. So if you're close to the supermassive black hole, your life will be very different. And the material is literally like, it doesn't just go around the black hole. I mean, some of the stuff goes around the black. I mean, we even go around the black hole. We are orbiting the galactic center. We've gone around the galactic center just over 20 times. So in that sense, in the galactic age, we're only 20. The sun is only 20 in the galaxy. But if you're closer, some of your material could literally like be taken out and falling into the black hole, making it more and more massive. And that falling material will be going through a lot of acceleration. We will talk about some of the processes like synchrotron radiation. So these processes of that material falling is what we can see and what gives off the radiation in the radio waves and the X-rays or whatever. So that's what makes it bright around the supermassive black hole, okay? It's not infinitely massive. We will talk about how massive it is. So, real quick, how does a galaxy form? So, we talked about how in the beginning of the universe, basically we just had mainly photons. It was a radiation-dominated universe. We had photons, positrons, and electrons in the cosmic plasma. And we also had neutrinos and very little baryons. So there were no stars, no galaxies, no nothing like that in the beginning. The universe itself has gone through a lot of evolution is something I want you to appreciate. So there were no stars, no galaxies, no planets, no us in the very beginning, okay? So it really has kind of developed over time. It used to be radiation dominated, lots of photons, exciting everybody, hot and too much energy. Nobody can calm down and become neutral type of situation. And then slowly, after making a little bit of baryons, much later, we started to make the first generation of stars and whatnot. And, gravitation is an attractive force. So sort of material forming, stars ultimately dying, enriching the medium, more stars forming. And this has been happening for a long time because like we have so many galaxies at this point, and each galaxy, I mean, our galaxy has 200 billion stars. So we've come a long way from like, we're almost 14, the universe is close to 14 billion years old. So we've come a long way from that Big Bang state of things. So from the cosmology point of view, there's a lot to kind of wrap your mind around in terms of the evolution. It's important to understand. The other thing that you asked about galaxies forming that we still need to research is the role of dark matter in galaxy formation. So what we saw with cosmic inventory is that right now in the evolution of the universe, most of the contribution to the critical density of the universe is dark energy, followed by dark matter. So putting dark energy aside for right now, because dark energy is involved in the expansion of the universe, and it is especially important at very much large scales. If you're considering something like our own galaxy or the neighboring galaxies, then the important thing will be dark matter. So dark matter is a phenomena which is to be noted at all these different scales, at our own galaxy scale, the neighboring galaxy scales, the overall universe scale. Whereas dark energy, that's felt at very large distances, as in we see the universe is expanding at a large, when you look at it large scale, okay? So it's very important to understand. So both are open questions, the dark energy thing as well as the dark matter thing. Both are open questions, as in we don't know exactly what these things are. But to your point of asking about the galaxy formation, dark matter is extremely important because we think, we don't fully understand it, but we think that yes, all the baryonic material, the ordinary matter, which is what you and I are made of, protons and neutrons, all the elements, all of the stuff we've been talking about with the stars and everything like that. There is, of course, attractive force of gravitation, working to keep these things within whatever geometries that they're in within a galaxy or whatever. But we think that dark matter could also have a big role in galaxy formation. And stay tuned to learn more about that because it's an active research area. And if we, people who learn about galaxy formation and structure formation in the universe, that's a very relevant topic. Okay. The kitty cats are fighting. So now we can talk about, so the elliptical galaxy, it's simply based on morphology. It's just a shape, spiral versus elliptical versus irregular. It just has to do with the shapes of the galaxies. And of course, certain things are also different, like what type of stars and what types of things happen in each one is kind of different. Bye, Sundar. Good night. Okay, we will talk about the supermassive black hole. Sorry about the various... yeah, let me talk about it. So at the distance of the... Or sorry, let me make sure. Is this the part where... There we go. There we go. So let's talk about Sagittarius A. So, oh wow, we got 20 legs. At the center of our galaxy is a strong radio source called Sagittarius A. So now keep in mind these differences. There's a few different names that I want you to pay attention to. Sagittarius A is not the black hole, okay? The name, the black hole is Sagittarius A star. Sagittarius A is a strong radio source. Of course, these are all relatively close to each other, but yeah. Okay, so let's talk about this. At the center of our galaxy is a strong radio source. Actually, one second. Can I need to reheat the hot chocolate. I'll be right back. And then we'll talk about Sagittarius A. Cosmic plasma, somebody asked about that. Cosmic plasma, when we say what is the cosmic plasma, it depends on when you're talking about. In the Big Bang type of timeline, the cosmic plasma was mainly photons, positrons, and electrons. And these things were pretty much in equilibrium, as in they're constantly interacting with each other, and they're constantly bumping into, and they're constantly being like in this hot, dense, energetic environment, not calming down at all. So that's what pretty much people mean when they say cosmic plasma during the Big Bang. And then we also talked about the neutrinos and how they kind of broke up with the cosmic plasma because the expansion rate was actually a little bit bigger than or faster than the interaction between the cosmic plasma and neutrinos. So, it's so we discussed that in our cosmology lives. If people are interested, please do go check that out. Like there's a lot of options to pick from during in the live tab, and you can find that. Think solar flares will knock out the electricity? Um, I guess, yeah, I guess that could happen. So solar flares probably contain charged particles. So depending on yeah, depending on what they interfere with, they could certainly do some damage. But at the same time, remember, we have a magnetic field. So we, it's some of it is redirected because of our magnetic field. So thanks to Earth's rotation and its iron core, we have a pretty good magnetic field, pretty strong one. So it will probably, redirect and divert the solar flares maybe towards a different country than yours. I don't know. You know what I mean? Let me, I'll be right back. 1 second. So, I wanted to talk about Sagittarius because, so there's the Sagittarius dwarf galaxy, not to be confused with our supermassive black hole. And there is the different parts of this galactic center. So the galactic center is what we're talking about, not just the black hole, okay? So this is cool. People asked about it. Hi, Suchi. Hi. Hello, can I sit down? So at the center of our galaxy is a strong radio source named Sagittarius A. I'm seeing if there's any other questions that I missed. Oh, somebody asked, do you think there is life on other planets? We will talk about that too. If there's a center, are we north? A center of... Are you asking of the universe or... So we are, in our galaxy, we're 8 kiloparsecs from the center. We're off to the side a little bit. Combat said, you never sleep. Superman says the earth is flat. Sorry. And then somebody asked about elliptical galaxy. We can talk about that. So somebody asked about falling into a black hole and would that cause a reaction? So basically, when you're close to a black hole, you will experience tidal forces on your body. So in short, depending on how you're oriented, you will feel these tidal forces differently. So depending on the mass of the black hole and your mass, there is a way to fall in where you would not be crushed as badly until you enter the black hole. Then, and you'll still be crushed. The death is still certain, but when exactly it happens can probably be strategized. So that's what I meant, Farouk, and we can talk about that math, that particular section as well at some point when you're back, because we did mention it in the past, but I don't know if you're still around. Whenever you're back at some point, I can cover it if I'm correct. Okay, so now, because Sagittarius A came up, we will talk about it. Did somebody... Oh, so MC24, did I answer your question, or was there another one that I missed? You make me want to wear glasses. Huh. I'm trying to see all the actual relevant questions, and it's kind of hard. Ooh, and also, yeah, elliptical galaxies are basically ellipses. Like literally the shape is an ellipse. And so they're like sort of this bright blob of an elliptical shape with different ellipticities. And we talked about how the ellipticity is used to further subclassify them. And they have more entropy, like we were just mentioning, as opposed to the spiral galaxies. And there's some other things too that we can talk about as far as like differences. And we looked at some example ones. So I think one of my afternoon lives, one of these days, we talked about the elliptical galaxies and irregular and spiral galaxy differences. So you should find that live, Stephen. There were some really pretty pictures I think that you would like. MC says, I don't remember. Okay, that's fine. So at the center of our galaxy is a strong radio source called Sagittarius A. So remember, we haven't mentioned the black hole yet. It's just Sagittarius A. The total region of radio emission is about 50 parsecs across. The spectrum of the radio emission indicates that it is synchrotron emission. So I was mentioning how things falling in probably do that. Why is the universe expanding? We talked about this last night, but good question. We will talk about it again. The spectrum of the radio emission indicates that it is a synchrotron emission produced by a relativistic electrons accelerated by a magnetic field. So these materials that are falling into what we will just now talk about is basically getting super duper accelerated and falling in at a relativistic speed, and relativistic electrons radiate the synchrotron radiation. So the long prominences stretching away from Sagittarius A resemble solar prominences. So sort of like the solar flare stuff that people were asking about, scaled up by a factor of 1 billion. So imagine something like solar prominences, but times a billion is what's kind of happening here at the galactic center. So the galactic center is, of course, a very extreme place. It's a good thing we're not very close to it. We're 8 kiloparsecs away, and the entire galaxy from one side to the other is around 30 kiloparsecs. So that tells you we're not really towards the center or too close to the center. So the early radio observations that detected Sagittarius A were of low angular resolution and merely revealed the presence of an unresolved blob of radio emission. More recent observations have found detailed substructure in Sagittarius A. So we knew that Sagittarius A was this big radio source. That's all we knew. We haven't yet, let's say, found the black hole yet. We know that there's this presence of an unresolved blob of radio emission. Now we know that the radio emission is probably the synchrotron radiation. But at first, astronomy is all about the observations. If you see a bunch of radio emission from a certain direction, you're like, oh, okay, I guess that's something is right there. So you get these blobs of things, and then you have to further look and further think and further investigate, right? So more recent observations have found detailed substructure in Sagittarius A that we didn't have before. So far so good, Sagittarius A. If we zoom in on the highest surface brightness region of Sagittarius A, we find an interesting radio source called, called Sagittarius A West. So far we've got Sagittarius A, a bright radio source towards the galactic center. And then we have a substructure called Sagittarius A West. So since the thing was already called Sagittarius A, we just tack on another word, west, to classify. Sagittarius A West is a rotating mini spiral of partially ionized gas, which is about 5 parsecs across. So the whole thing, the full thing is 50 parsecs. The whole thing is 50 parsecs across, but Sagittarius A West is a rotating mini spiral of partially ionized gas about 5 parsecs across. Its radio spectrum looks much like that of an H2 region, in which gas is excited by a central source of ultraviolet light. In the case of Sagittarius A West, the central source must be very luminous, but what is it? So far, we know Sagittarius A, the bright radio source. We know Sagittarius A West, rotating mini spiral of partially ionized gas, and radio spectrum looks like, looks like something else that we kind of understand. It's all about the spectrums and the lines and stuff, right, in astronomy. So it's like, oh, that looks like this other thing we know. So if we zoom in on the center of Sagittarius A West, we find a highly compact radio source called Sagittarius A star. So it looks like Sagittarius A asterisk, but it's not an asterisk where you get a footnote. It's literally called, the pronunciation is Sagittarius A star. So that's the black hole, okay? The angular size of Sagittarius A star has been measured using radio interferometry. At a wavelength of around 7 millimeters, the measured diameter of Sagittarius A star is around 0.8 milliarc seconds, corresponding to around 6 astronomical units in physical units, right? Where 1 astronomical unit, remember, is our distance from the sun, Earth distance from the sun. The high angular resolution provided by radio interferometry also enables a measurement of the proper motion of Sagittarius A star. Recent measurements reveal some more differences that we've found of around, let's forget those numbers, that's too specific, but basically there is sort of a proper motion measurement that they're doing, and it's directed almost entirely along the plane of the Milky Way. Oh wow. If Sagittarius A star were perfectly stationary at the galactic center, so if it didn't move at all, we would expect the sun's motion about the galactic center to produce a proper motion of around 5.8 times 10 to the minus 3 arc second per year, whereas we see that it's actually 6.38 plus or minus 0.02. So there are some detailed measurements that tell us more things that are kind of like a lot of detail, but that was some radio stuff and some other types of things that we found just now. Now think about, now there's also more measurements. This is now going to be in X-rays. So the Chandra X-ray Observatory, I don't know if you heard of it, it's kind of like a famous X-ray observatory. There are also observations by that, Chandra X-ray observatories, which found that Sagittarius A star is an X-ray source as well as a radio source. So it's not surprising that it has multiple types of emissions, but around it, but we found it with a whole another observatory as well. The X-ray emission from Sagittarius A star the X-ray emission from Sagittarius A star varies significantly on timescales of less than 1 hour, revealing that the majority of its X-ray emission must come from a region less than 1 light hour. The time it takes for the distance light travels in an hour, that is. So, which is around 7 astronomical units. So, because guess what? We know that it takes around 8 minutes for the sunlight to come to us. So, light, the speed of light in vacuum is a constant of nature, and it is finite. So, even the sun, light, which only has to travel 1 astronomical unit towards us, takes around 8 minutes, okay? So this thing, we're trying to figure out what exactly, how big or and whatnot, but the X-ray emission varies significantly on timescales of less than 1 hour, revealing that the majority of its X-ray emission must come from a region less than 1 light hour across. 1 light hour, an hour in the distance traveled by light in an hour is around 7 astronomical units. Let's review what we know about Sagittarius A star from all of these things, because we still are just observing things. It's fairly luminous, but highly compact. So for how luminous it is, it's highly compact. 7 astronomical units, not that big in terms of how big it is, how luminous it is. Let's review what we know. It's fairly luminous, highly compact, source of radio and X-ray emission located at the galactic center. So the bolometric luminosity of Sagittarius A is not exactly known due to the high extinction at many wavelengths, but is estimated to be around 1,000 solar luminosities. So it's very, very luminous. So from all this, so if something is super luminous, as in the surroundings of it, super luminous, but the thing that seems to be, well, it's super luminous because the stuff that's falling in, that's what's creating all the luminosity, the brightness and radio and all that. Now the stuff that's falling in is obviously, I mean, it's going into the black hole, right? So it pretty much makes the black hole be luminous, although strictly it's the stuff that's falling in that's making it luminous, if you will, you know. But because the distance associated with the brightness is pretty compact compared to how luminous everything is, that's why we have this leading hypothesis that Sagittarius A star, the pronunciation, is a supermassive black hole that is accreting gas. So when we think about it and we think about what could be happening, and we see these observations, we pretty much think that the only way to conclude this is that it's a supermassive black hole that's accreting gas. It's eating material from its neighboring objects and making gas fall into it at such an accelerated way, where then we get synchrotron radiation and all this ionized gas emissions and things like that in radio and X-rays, making it a very bright source in those wavelengths. A supermassive black hole is a black hole larger than would be a result from a massive star collapse alone. So this is the difference between a normal, I kind of mentioned it earlier, but this is the difference between a normal black hole and a supermassive black hole. A normal black hole is a stellar remnant formed when a star dies, when, depending on the mass of the star, you either get a white dwarf or a neutron star or a black hole. So that's a normal black hole. But a normal black hole would not be this big. When a black hole continues to eat a lot of things and gets fed by its neighboring objects like this one, then it starts to get a lot bigger and more massive. So that's what's going on here. The mass, so there's some interesting math here, a little bit, I'll cover it. The black hole hypothesis is testable by looking at the motion of the stars in the vicinity of Sagittarius A star. If there's a black hole present with mass of MBH, much greater than a stellar mass, then stars on elliptical orbits around the black hole will obey Kepler's third law. So from all of that, we get oh my gosh, are you ready? Are you ready to know the mass of this supermassive black hole? It's around 3.7 times 10 to the 6 solar masses. That's how big this supermassive black hole is. It's a lot of mass. So by just doing Kepler's law stuff with the orbital motion of stars nearby around the black hole, we're getting around 3.7 times 10 to the 6 solar masses. So it's like over 1 million solar masses is the supermassive black hole. That is That's very extreme. Like hundreds of solar masses, thousands of solar masses, that would be one thing. This is 3.7 times 10 to the 6 solar masses. That's the mass of that supermassive black hole. Wow. If a star... Ooh, also we talked about this. If a star is swallowed whole by a black hole, it doesn't produce a major outburst of radiation before it enters the event horizon. So this is the stuff, the tidal force things I was talking about with people too. Whether a black hole swallows a star or a people, how you fall in is important. If you fall in a way where you just kind of dive in, then you disappear, you're swallowed whole, then there won't be too much radiation and drama. And you will get to see the inside of the black hole before you die. But if you're tidally shredded first, whether it's a people or a star, then we will see that as a signature, probably depending on, how much stuff falls in and how bright it is. If something is tidally shredded in the process of falling into a black hole, then we get all these signatures. So we are kind of lucky that the supermassive black hole at the center of our galaxy is doing this tidal shredding and accretion of material into it. Because if something just falls in directly in a way where you don't get all this accretion, then you wouldn't see all the brightnesses from those things. So if a star is swallowed whole by a black hole, it doesn't produce a major outburst of radiation before it enters the event horizon. And remember, once something is inside the event horizon, you can't see it. That's it. It's not coming back out and you can't see it. However, if the star is tidally shredded first, its gas forms a hot accretion disk around the star and produces copious emission as it spirals in toward the event horizon. So it's really about it's almost like the stuff is merging with the black hole, just like we talked about the tidal tails of two galaxies merging. Same thing here. Ultimately, it's all about how someone falls into something. Are you tidally shredded? Do you have a tidal tail? Do you just get swallowed whole? Depending on that, you would get copious amounts of emission or not, and your death will be visible in different wavelengths of light or not. Okay? I must admit, one of my favorite Disney movies as a kid was a movie called The Black Hole. Very nice, yay! Can we get 30 likes? I thought I had more likes. Now I look up and there's not that many. So, we can next talk about quasars because I keep promising that I will and then I don't. We can talk about quasars. How is everybody doing? Wait, ooh. So by the way, large Magellanic Cloud and small Magellanic Clouds are two irregular galaxies. Okay. And the large Magellanic Cloud has many young stars, some of them massive, and is host to the occasional core collapse supernova, like 1987 A. So 1987 A is from that particular irregular galaxy as a supernova. Example. Awesome! Steven says he's good. Okay, where is my quasar chapter? Okay, so as far as the active galaxies go, we have Seyfert galaxies, quasars, and radio galaxies. We will talk about these. These galaxies may have an active galactic nuclei, or nucleus, rather. Seyfert galaxies and quasars are actually quite similar to each other. Seyfert galaxies can be thought of as low luminosity, relatively nearby quasars. Radio galaxies are different in that their nuclear emission often is not prominent in wavelengths other than radio. So they may have a lot of emission, but just not in much else other than radio. And so we will talk about these types of active galaxies. And one more time, we will talk about what we mean by active galaxies as well. Okay. Thank you. Okay. So, active galaxies basically produce a lot of non-stellar emission. So, some of it is non-thermal in origin, arising from energetic and violent processes. And active galaxies produce more radio and X-ray emission than you would expect if all their light came from the photospheres of stars. So lots of radio and X-ray. So we were just talking about radio and X-ray emission from our own galaxy's center, right? Sagittarius A. And then we learned about the Sagittarius A star black hole, of course. But yeah, so our galactic center is pretty active in that sense. But there are galaxies that have even more of this type of activity. So active galaxies must have much of their light concentrated in a small central region known as an active galactic nucleus, or AGN. So you might have heard of AGNs. That's what this is, active galactic nucleus. Light from AGNs is variable on short timescales at virtually all wavelengths. The timescale for significant variability is dependent on both luminosity and wavelength, with the most rapid variability seen at shorter wavelengths in lower luminosity AGNs. So it makes sense, like shorter wavelengths would mean higher frequency, higher energy. In low luminosity AGNs, X-ray emission can vary on timescales of minutes. Some active galactic nuclei have jets that are detectable at X-ray, visible, and radio wavelengths. The jets contain ionized gas flowing outward at relativistic speeds. So this is interesting. We just talked about ionized gas when we mentioned the Sagittarius A star, or the Sagittarius A system, right? So some of those same things are happening here. The ultraviolet, visible, and infrared spectra of AGNs are dominated by strong emission lines. So lots of emission in these types of spectra. So, yay! Next part will illuminate exactly what I was saying earlier. The accumulated evidence indicates that the activity in galactic nuclei results from the accretion of matter onto supermassive black holes. So active galactic nuclei also pretty much involve supermassive black holes, and most, if not all, bright galaxies harbor a supermassive black hole at their centers. Although bright galaxies contain supermassive black holes, not every bright galaxy is an active galaxy, right? Because there could be a ton of stars that are contributing to the luminosity, like in our galaxy. It's not just the active galactic nucleus that mainly contributes to the luminosity. A supermassive black hole is a necessary but insufficient condition for activity in galaxies. To be classified as an active galaxy, the central black hole must be accreting gas sufficiently rapidly to have a luminosity high enough to compete with or outshine the stars in the host galaxy. So in other words, if you have a ton of bright stars and those are the main contributors of the luminosity in the galaxy, then we don't consider the galaxy to be an active galaxy. I would say our Milky Way galaxy is pretty active, but it's not classified as an active galaxy because we also have a ton of stars and, you know, diversity. We are a more wholesome galaxy, where just the activity, you know, because of Sagittarius A is not the only thing that's contributing to the significant luminosity. There's lots of other things going on as well. But if you have a galaxy where most of the luminosity can either compete with, or sorry, the luminosity of the active galactic nucleus can either compete with or even outshine the stars in that host galaxy, then you would consider that an active galactic nucleus or an active galaxy, and fall into this sort of category. I thought Andromeda was just a spiral galaxy. Is that not the case? M31, we can Google it. Let me take a sip of this. So active galaxy is where the luminosity of that stuff, so it's a good thing we talked about our supermassive black hole just now before we started on this topic. Our galaxy would be considered an Jade. Hello, Jade. How are you? Our galaxy would be considered an active galaxy if all that stuff we just mentioned with our supermassive black hole, the gas falling in, the electrons accelerating, producing all that radiation and emission in radio and X-ray, if that luminosity of all that outshined the luminosity of our stars, or could compete with the overall luminosity from all our stars, then we would be considered an active galaxy. But if we are a wholesome galaxy of other things happening as well, and plenty of luminosity coming from plenty of stars and things, then we would be not considered an active galaxy, or a galaxy that is associated with an active galactic nucleus. Yeah, so Andromeda is, yes, that's what I thought too. Andromeda is just a spiral galaxy. It's not considered an active galaxy, as far as I know, but please fact check. So now we will talk about quasars. So radio telescopes first surveyed the sky in the mid-20th century. These first surveys showed that the optical counterparts of most radio sources were galaxies. The radio galaxies discussed later on, we will discuss them later. However, some radio sources did not have obvious counterparts. Ambiguity arose because of the poor angular resolution of single dish radio telescopes. Thank you for liking the live. Yes, it's a barred spiral galaxy. Awesome, thank you. Actually, I need to blow my nose, and then this hot chocolate is cold again. I'll be right back. We will finish up quasars tonight, don't worry about that. I'm nuking stuff again. BRB. So, once better radio positions were obtained, it was found that the radio sources were associated with blue star-like objects. Blue star-like. Okay. I'll be back in one moment, please. You can watch Suji Mama for a second. Turn up the heat here.